Welcome, and thank you for joining us for the January Colloquium. It is my pleasure to introduce Dr. E.K. Esawi, today's speaker. He came to EOU last year as an associate professor of data analytics, and he coordinates our new data analytics program. He came here from the University of Charleston in West Virginia, where he oversaw a similar program. He holds graduate degrees in applied mathematics and geoinformatics and computational science. His research interests include environmental and geospatial data science and signal and image processing. Today, he'll be talking about applications of data analytics in heat flow in natural systems using an example from Yellowstone National Park.
No? Yeah, it sounds like good. I use the terms data science or analytics are in the same, they're interchangeable. I'm going to, I think, why some people say what data analytics has to do with the Yellowstone or heat flow or anything. And data analytics is just like any math subject or statistics is you need a medium in where you apply whatever you have. And so this is a very good, my talk is going to be 3 parts. The first part is about a paper that my PhD supervisor and I published about 10 years ago. And the second, then I published the paper after that on my own. And then about 2 months ago, 3 months ago, we have a paper in review. And I decided, or my advisor and I decided to do some little bit more work that I'm still stuck on it. So if anybody can help at the end, that will be good. Like I said, the first part is going to be very brief about heat flow and simple equation, not too much math in it. The second part is I'm going to talk in general about data science, just very, very basic things. And the third part is I'm going to talk about the research project that I'm working on. And unfortunately, because I couldn't use my computer that has certain software, I have files that I was going to show. So the third part probably is going to be too much blabbing, but I hope you catch what I'm talking about. All right, modeling in heat flow in natural systems. So I would ask, have you been in the Yellowstones? How many of you have? Looks like lots of you. That's very good. Then I don't have to say. So what's a model, especially in the physical science sense? I often give an example, like if you have somebody who had never seen a car and you show them like a car model one, then when he or she see the real car, they can see the similarity between them. Although physical models is using more, I guess, physics, goes without saying, and the aim of models in general is to estimate or approximate certain phenomena or certain things. Why modeling? Why do we need to model anything? Well, we need to model anything because we want to understand them. Sometimes you have no other way to understand lots of these phenomena without developing a model. And then how good is our model? You can have a model, I have a model, and which one is the best? And at least within this context, the best one is the one that approximates the data best. In other words, if you have an observation or if you have an experimental data and you want to figure out, can I model this data and see if whatever assumption you made and all that kind of things, does that produce or match the data that you saw? In fact, somebody remind me, it's not me, like, I don't know, years ago, there is a Nobel Prize winner, I think it's called Higgs bosons. I don't know if some of you may remember. And I remember their theoretical work was long time ago, and they tried to publish in so many journals, and they told them this is complete nonsense. In 2010, I believe, or 2015, I don't remember, experiment results matches their model, and they won the Nobel Prize for it. So, you know, it's all right. Basic eruption terminology. I think some of this is, most of you have been in the Yellowstone, so I don't need to go that. And that's usually when you have an eruption, you have the date and the time. You have duration, and that's the duration is basically we're talking about how long the column of steam and water remains. How long does it stay up and then it cools down? Then the PrePlay, and I'll just go. And so these are the 5 variables that for any geysers. The duration, as I said, is the time interval that you have the column of water if you sit in the the Old Faithful, and that usually is not too long. And then the PrePlay is, this is just when you see everything is calm and nothing happening, and just a sudden you see bubbles, you see like some steam coming out, and you see water and more, and then the volume of steam increases until it gets bigger until it explodes. So that is just before it explodes, that will be the PrePlay. The interval, like I said, is the difference between any 2 consecutive eruption, and the height is the height of the column of water, and usually it's not, a lot of them, they are kind of approximate, and I will talk more, but especially height, no one really determine exactly, at least a few, how high the water goes up. This is just a website that I will show you earlier. Snapshot of the original data. As I said, because I couldn't bring my computer, so where does the data is at? There is a website called GOSA that stands for Geyser Observation and Study Association, and those are still, the website is still there, but the original data that I will talk about shortly, that wasn't there anymore. That was moved to the geysertime.org, and these are, in both cases, these are mostly geyser enthusiasts and stuff like that, and they go and watch geyser and do all that stuff. So this is a snapshot of the data. As I told you, the date, the geyser, the time, the interval, the duration, the PrePlay, and the height. And in this, as you can see here, these numbers are at least reasonably consistent. And because it's mostly for Old Faithful, and Old Faithful is the geyser that has been probably studied more than anything else. There is an incredible amount of data on it, and so the data is a little bit more consistent, plus some of the data is collected electronically. In other words, and when it's collected electronically, it's a lot more accurate than, as you can see these little things, IE, and you see here plus, and you see these, especially for other geyser. And so this really represents a clean shot of the data. It's just at least, and I don't know, those of you who use Excel, I have this habit of, I always insert a column and I call it OO, and O stands as here for me is the original order. So if you fall with any spreadsheet and you do all different kinds of things, and then you forget what your order is, because Excel really doesn't keep very good order unless you have any columns. So I do that way. It makes life a little easier for me. Okay, an example of a model. This is, might surprise a lot of people, but if you have the water comes up from the ground, clearly there is at least a space that the water comes from, but what that space looks like. How do you calculate the volume that comes out of that space? And here is why my advisor is the best model he could have come with. And clearly there is nothing like this in Old Faithful, like a big, all nice hole is. And as he, oops. All right, here we go. This is, and I assume everybody knows why you have, geyser is just because we have hot material at the bottom, and that hot material is very, very close to the surface. In fact, I will talk about it a little bit more later. the Yellowstone is one of the most monitored part of the United States, probably as much as, if not more, by the San Andreas Fault, the fault that goes in the West Coast. And talking about fault is actually my advisor started his work is try to predict earthquakes. And what he does is he studies heat flow, as I said before. So he goes to like a lot, especially the San Andreas Fault and a lot of others, the active fault, and he will look at it clearly when you have an earthquake, the ground just shakes and slides against each other, and if it does, it generates an incredible amount of heat. And that heat it kind of gives you an idea about previous, like paleo, temperature, it gives you a lot of old information. All right, basic equations of heat flow. This is, I realize this is a public, general lecture, so, but I can't help, like you can't give a talk without some equation if you have some deal with mathematics or statistics. And so before I show is, I only show you here, this is not a heat equation. This is basically the really probability density function. And you will see shortly why we don't have to worry about, I said the equation, but you will see shortly here why we use this equation. These are, I'm just going to go very quickly, Newton's law of cooling. That is what my advisor used to model. This is a simple differential equations, and you solve it. He solved it, and then he put all his assumptions, run a program, generate a data based on the model, and then he compared it with the data we have. So those are very just, and now here is what I did. So you can see why we said Rayleigh distribution. So this is here, oops, sorry. These bottoms are pretty close to each other. So here is the PrePlay time. As you can see, it's reasonably a Rayleigh type distribution. In fact, that's what I did myself. I did a lots of work on it, and we're trying to figure out what kind of distribution we have based on the data we have. And we settled, but lots of back and forth discussion with lots of people and with lots of statisticians, and we thought that will be the proper distribution. And as you can see here, N is 17,000. That's the number of data points we have. And now this is the interval distribution. This is what they call bimodal distribution. In other words, you see some interval it go very, very long. It almost like go an hour and a half. And some of them, they go about an hour. So there are like the interval is not the same all the time. We have what we call it bimodal. And here is again the distribution for the duration. Again, it looks like it's a bimodal. It looks like it goes sometimes between 4 and 4.5 minutes to about 2 minutes. And now the next slide is maybe the most important slide, and let's take a look at it. And as I said, you can see here the black dots here. That is the data, and the red line is the results of the modeling. And as I said, so this is very reasonable. They are kind of consistent or reasonably consistent, the model data and the original data. And because it's the consistency here is the paper was accepted without any issues, and in fact it's been referenced reasonably, many, I don't remember, I don't count, I don't look at it, but it has been referenced a lot. Because like I said, the model, and I've seen lots of people do some work like this. So that is the part of the heat flow. So now we're going to move into the part of data science. So what is data science? And since Steve is here, we have to be, I thought he's not going to be here, so we can just count computer scientists as a completely outsider. But since I figured he might be here, so we gave a very good definition that inclusive of everybody. Data science is, in a way, like a statistics sometimes. Is lots of people claim it, mathematicians, statisticians, computer scientists, engineers, everybody. And it, in a way, it's rightfully so. It depends. It's a huge subject. It depends on what angle you are coming with. This definition comes from a person who is slightly more in computer science than in data science or statistics. And I was going to color the insights that in red, because that is really what generally data science is. We are looking for trends, we are looking for insights, we are looking for certain things that you cannot see it if you just do it in your own. And now I'm going to show you something here. Let's see, it doesn't do anything. Huh. Yeah, this is a link. What? Well, this is a link. It should just, yeah. It's not, it has nothing to do with the PowerPoint here.
He's saying maybe it's already there if you close.
Oh, I see, I see.
You got a full screen.
No? Well, I guess now I have to blab more than I had planned anyway. I'm going to try it one more time if I can. This is. There you go. This is something familiar to most people. You may not remember it anymore, but this is, and I'll shortly tell you why this is a periodic table. This is the table of the element, and that has been done long time ago, at least it started, and all these elements are listed by atomic number. It's just like whole number, 1, 2, 3, 4, and you know. And this, the first attempt, or among the most important attempts, that's done in the late 1800s, I believe, around 1870, by a Russian chemist. And all what he was trying to do is, at that time there were very few elements, so he's trying to organize them. He's just trying to put them like in a list. And I don't know, he was definitely good enough, I'm very sure he was lucky, I suppose. And he noticed something, and like keep in mind, he didn't have all these, like all these that came after, lots of these boxes here, they were empty. And so what he noticed something that, like I said, if you have numbers, you put them in a column in a row. What he noticed that if he goes like in a column, we go like this, he then not only have the atomic number increases, but he has the chemical and physical property of every column are the same. So what he actually said and told people is, let's say at his time, let's say this element is not there, this element is not there, a lot of these elements is not there, but you have this element, for example, and this element. Well, guess what? That means this box is empty, this box is empty, a lot of these boxes are empty. You know what their atomic number, and you know what their physical and chemical property, you just go ahead and discover it. Now, this is what the American Chemical Society says. This is one of the greatest data science attempt that ever been. Of course, they, that from it, but it's really a good thing. Can you imagine if he had, instead of probably he had, I don't know, 10, 15, or 20, can you imagine if he had like 1,000 or 2,000? Would he have been able then to, figure out or just see these insights without, you see the point here, folks? And that's why they call it, and to a certain degree, I agree with them. Because that's the, like I said, if you imagine if you have 1,000 or 10,000 data points, that would have been very difficult to predict what kind of property or what kind of patterns you have. And in the most general way, like I said, this is what data science does, or it should do at least. So example, and these are some of these examples may not be good one, and they may not have to do completely with data science, but it do something, you know, whether data is clearly health data, financial data, and spatial data. These are all data. And then I'll go here with the foundation of data science. And here is where lots of people may agree. Now, Steve, we didn't mean to put you the last one here, but the order is not important here, just so you know that. Okay. So the foundation, these are usually the three, the statistics, the applied mathematics, and the computer science. Sometimes I've seen programs in data science that are exclusively computer science. They may have one or two statistics, or sometimes they don't, and the other way around. I see a lot of data science programs that have all the statistics, and maybe they have, in fact, I just saw one, they don't even have a programming language. So it's, those are the general, and a plus anything else. So what I mean plus anything else is, if you do a data science, just like this talk here, you have a standard, you have a set of universal tools, you know, machine learning, blah, blah, and all these kinds. You can apply it to anything, but you need a medium in where you apply it. And you have to not only know the basic principle of these things, but you have to know, at least familiar with the medium where you're going to apply these things. What are the major subdisciplines of data science? They are machine learning, data mining, visualization, modeling and simulation. And I'll give an example here, but there are a lots of overlap among these things, and sometimes it's hard to know which is which. Lots of people just recently, I was looking at a book, a new book about, and he includes machine learning as a part of artificial intelligence. Some people will include artificial intelligence as part of machine learning, and they are all kind of, like I said, they have a lots of overlap, just like physics and chemistry. It's almost like that overlap, the line is, you don't know where it stands. Example, like I said, those are, I don't know if that's a good example or not, but it's a little bit, smart cars and spam folder. This is probably, oops, this is a spam folder, at least it's one of the early things they do in machine learning is, or statistical learning, if you will, and they will train, the program or the algorithm. So, these type of are spam and these types are not spam, but we all know sometimes what we thought spam wasn't really spam and vice versa, but that's the nature of things. So who can be a data scientist? This is, well, here is an old definition. This is a quote from a very famous data scientist at one time. He puts it, one who knows more statistics than a computer programmer and knows more computer programming than a statistician. And I have no idea what that means, but then this is not a new definition, but this is maybe what is maybe today's definition, at least maybe at the undergraduate level, that one who has a basic background in statistics and applied mathematics and strong programming skills. If I had known Steve is here, I would have put it computer skills, but sorry, Steve. And then there is the ideal definition, which is one who knows statistics, applied mathematics, and computer science, and that's no one does. Because often people ask me, who can be a data scientist? Or what can how do I become a data scientist? And my answer is always, learn as much as you know about the statistics and applied mathematics and computer science, and you will be. But like I said, we all have limited time in this earth and time to study, and therefore a capacity to learn all these things. And so most people, like people who wrote books and people who, well known in the field of data science, what they do is they have dual degree in two of those, and they learn the third one in their own. That's what most of them. In fact, I taught, and I hopefully soon will teach a machine learning course, and I use a book, And the people who wrote the book are all statisticians. And what they did is, they, in fact, I don't know, some of you may be familiar with this book. It's called Statistical Learning with R, or Introduction to Statistics. I don't know, Steve or anybody, you may not have heard of the book. This is written by a couple of people from Stanford University, 3 or 4 of them. And they are a statistician by training, and so they did a lot. It's almost all of it is statistics. They talk very little about computer science. But they use R, and I was talking earlier for, R is a huge ecosystem that, you can do all different kinds of things in it. And so, like I said, it depends. I also know, or I'm aware of one person who, again, teach like a course, like, again, in machine learning, and they use no statistics. It's completely computer science, and they do a lots of databases and that. Okay, so now that's my, I suppose, marketing effort for the data science program. I hope that was successful. And then now I'm going to go with the next, the project that I'm working in right now. So why the Yellowstone is that, like I said, most of you have been there, so I don't need to tell you. But it's, and that goes without saying, data availability. And I'm going to talk a lot about the data availability here shortly. Public interest education. This is really something what surprised me. When we submitted the paper that we have in review, my advisor talked to the editor, and the editor really likes some work in the Yellowstone. And when he asked him why, he said, because this is public interest. We would like people to go to the Yellowstone. We want to know, we want them to know about the Yellowstone. We want to know, yeah, some of the research may be a little bit abstract for lots of people, but some of it they can learn it and they can do it. So it's something that has a public interest in it. One of the most monitored places in the USA, and it is true, and the reason obviously very clear. You have lots of hot stuff, and you never know when that hot stuff comes up to the surface. And you definitely, so I think there are about 3 or 4 federal agencies that collect incredible amount of data in the Yellowstone. And they watch it. This is the federal government, but there are also private people and stuff. Potential energy source. I was talking here, just, I don't know if any of you are aware, but you know that you can pretty much heat your house from the ground. And what I know, at least one family that they have a house in the Midwest where they just drill down, and if you drill down, can maybe tell you something that you will never hear in any other seminar. I was born in a part of the world where most of the houses in the above the surface, but we also have something underneath the ground. I don't know how to explain. Maybe I should have got a picture. But those places, even during the summer, they are pretty cool. During the winter, they are very warm. So can you imagine if you go like 50, I don't know, 50, 100 feet or so down, it'll be reasonably warm, and it's reasonably not that expensive to use it. And so this is a place, this is like a laboratory for thermal energy and all that kind of things, because if you can't do anything here, you can apply it in other places. The data, and this is where I'm gonna, because I don't have my switch, so the data that was collected, and maybe first of all, I'll show you who collected the data. Who collected the data? Well, you watch this. And I'll talk a little bit about it, but even visitors, this is the Yellowstone, the park they started collecting data in 1970, and they have been collecting data since then. In the beginning, they have a book, and what they do is, park rangers, they go around and they write some notes and they put them in the logbook. In fact, they call it the logbook. Sometimes volunteers, lots of, or geyser enthusiasts, I guess the same, are volunteers. They go and look at these geyser and collect data and then put them in a logbook. And this one here that's the name of the guy, what he did from 1970 1979 to 2011, he mounted camera around lots of those geysers, and there are so many of them. He mounted a camera and recorded everything. He recorded, so that way you can know the duration, the interval, you can do it very, but of course he couldn't put it in like 40 or 50 or more geyser. And that is the data that considered, standard accurate data. The result was a complete miss, and that was true. And I got 1 million rows by 10 columns, and I'll just, like I said, since I can't show you, I'll tell you why it's complete miss. I mean, you just imagine if these people who collected, they individually collecting the data, that is going to be complete miss no matter what. At least, they are going to have different units. Some people will write even the time like a PM, AM, or some of them write it in 24-hour format. Some of them write 1.5, like an hour or a minute and a half, and some of them write it in some of them even write like 1/3 or 1/4. And when you write them in your little website, those of you who do any programming, that's nearly impossible to read. And so what my first step was, kind of like divide and conquer. What I did is with these all, I wrote a code that I wish I was gonna, my plan, I was gonna run the code and show you what the result, but as I said, you can do that. So, and I will just say very little for like when you read files by any software, and maybe I'll put a blog for Steve and other people. So if anybody wants to learn all this stuff and everything, you need to learn Python. That's a computer programming language that's very, very good, and it's, I believe even Steve told me one time, sooner or later it's going to be the #1 programming language all over. And when you try to read these things with a program, the program don't understand different things. So you just have to tell it what column is that. So if you tell it the column is, this is date and the format of the date, it will ignore everything else. If you tell it the time will be, let's say 24, it will ignore all AM and PM and everything else. At least that will give you kind of an idea. And so what that does is, but it takes the good pieces. So I took the good pieces, and then actually those are the one we use it in the paper we just told you published, and then the rest of them, I cleaned them semi-manually, i.e. I was using Excel, just using lots of formula for every batch. I use a different formula, and all what I did is standardize them. That's all what I did. Okay. Data discussion part 2. So starting with 1 million data records, separating the good from the bad, and that's my first step, and then determine the quality good versus bad data. And that is my current project, and in fact I'm kind of stuck with it. And I'll here again, and because I couldn't really show you the data, I'm just going to very briefly tell you what I did. And I have, after I cleaned everything, and maybe I should say, after I cleaned everything, I got 100 out of 1 million, I got 125,000 row of good data. Of the 150,000, 20,000 data, about 80 of them are from Old Faithful. And as I said, Old Faithful is one of the most monitored. They have a lot of good data. In fact, most of the electronic data that I mentioned is about Old Faithful. So now I have 50,000 data points or 50,000 records, and my aim would be, because you saw that, and maybe you'll be surprised about my conclusion here, I don't want to get ahead of myself, but because data is important, my aim is, can I figure out how good the 50,000 data that I cleaned, how good they are? If they are good enough, then I can publish it, and then people, now they have data, they can go and do more modeling. The problem is, it is very difficult to compare what the data I clean compared with the electronic data. In other words, the electronic data, and Steve, I want you to pay attention because I may need help here. The electronic data has rows, the number of record, it goes from 1,000 to 100,000 each. So I have two Excel workbook sheets, one for the logbook, that's one done manually, and one from the one done electronically for the same variable. And now I have to do all that programming to read them and compare them. The problem is, how do you compare 100 or 100,000 record with 1,000 from another part? And that is where I'm stuck. So here I'm just repeating, I got 120,000 record of good data. Of the 120,000, I got 80,000 record of Old Faithful. That means I still left with 50,000. And now is, again, two Excel workbook, each with 25 sheets. One book contains electronic, I said RTED, and I did it intentionally. That stands for Ralph Taylor Electronic Data, because if anybody goes to geysertimes.org, that's how you know the data that collected electronically and other data. And the other contained clean and non-electronic data. The RTD sheets contains between 100 and then the non-RTD sheet contain about 100 to 1,000. There are many repeated records, and this is really the important thing here. In the electronic data, there are, in other words, they recorded the eruption 4 or 5 times a day. But in the non-electronic data, you may have 1 or at most 2. So my first attempt to compare them is, I said maybe I compare the means, the mean of the both data set, but it's really impossible to compare the means, because one of them has very high variance, the electronic data. The other one, you don't know anything about the variance period, because you only have very few points. And the sheets are different column names. The task is, how good, bad are the non-RTD 50,000? How would you go about answering the above questions? And that is where I am stuck at the point. That's where I have done some, I thought I know a few statistical techniques to discriminate between, or at least determine if they are the same. Because if they are close, then I can argue that the clean data is good, and therefore it should be used for other modeling and stuff. But if it's not good, I'm not going to tell anybody, or I'm not going to even write anything about it. So that's the point. Why even trying to answer such a question? I've already answered that question. Is that because we want to do some modeling? And in fact, my advisor, the last time I talked to him, he said, if you get this data, that will be a gold mine for publication. So I'll see if that will work. Now is, this is just a snapshot of computer code. That's those of you who tried Python, looks like Python code, and it is a Python code. And that's what I wrote to do all the analysis, to do everything that I needed to do. Like I said, unfortunately, and it took me a lot. Some of you, maybe like Steve, can look at this code, and you can see here there are lots of repetitive stuff here. In other words, why? Because the reason like I said, I have about, I don't know, about 100 lines of code that did everything for me, clean the data, organize them. You can compare everything and everything else. But like I said, and I'm trying even to do some, like I was trying to compare, to do like box plots and see if, they are close, but I wasn't sure really how to do this. That's, like I said, where I stuck. I couldn't go any further. I'm still working in it, and I hope I'll get something out of it, but I'm not sure. The conclusion, like I said, is going to probably surprise you. And this is kind of a, let's see if that makes sense to you or not. Data is important because data is the new oil. That's not my quote. That is when data science about, I guess, I don't know, it depends on who you talk to, but in the last 10 years, somebody was saying why we need data and some big shots, and he said data is the new oil. I don't know if really data is the new oil or not, or I don't know how you compare it, but I think everybody agrees data is very, very important, and I'm not sure if it will become as important as oil, but I don't know. So that's it. I make it a little short. So with that, I'll stop. If you have any questions or anything, I'll be happy to.
I just have like a question, like how much time do you spend at Yosemite, or is it all remote?
Yeah, can you please use it, because I'm...
For questions, we have a microphone that we can pass around here, so just a moment.
Hi. It's just a basic question about how much time you spent in Yellowstone, or have you gathered all this information remotely? Have you spent time in Yellowstone? Is maybe my question.
No. You mean all the data is got from a website.
Okay.
I didn't collect any of the data.
Okay.
No, thank you. And it's, in fact, like I said, that data, or most of it, it's not there anymore because now they moved it from GOSA to the Geyser time. And really, if anybody interested in that, Geyser, the website called Geyser Time, one word, .org, it has all different kinds of data on it.
Other questions for our speaker? Yes.
So how can you say a little more about how you decide between good and bad data? Like what you don't have to go very technical, but like what criteria you use to distinguish them?
Well, yeah, you're right, and I think the reason is I've been talking to other people, and I cannot, like if you can do, lots of other things if you are comparing the same thing. If you are comparing like sample, you compare population, you're comparing. The problem is with this is they are completely, you have, yes, they are data about the same thing, but we want to measure how close the clean data to the electronic data that was considered by everybody as the standard correct data. And like I said, I couldn't do anything technical or statistical or anyway where I can tell whether they are close or not. I don't know if that answers your question or not.
Yeah. Thank you. Questions?
So, EK, I'm just wondering what uses have you seen people make of your data collection and analysis? What are some practical applications?
Yeah, that's a good question. What happened is, as you can see here, our model is only done about Old Faithful because there were lots of data. There are about 40 or 50 other geysers that there are some data on them, and if this data, it becomes, if we can prove that is a good data, then it can be used by others, just like the beginning of this talk, where now you have a data, let's say about the duration or the interval or the PrePlay of another geyser, see if you can model, see if you can, your model data or model result will match the data that we have. Because there isn't a lot of data in other geysers, and that's the aim of putting this together.
Just a comment. It seems to me the problem you're studying could apply to many other citizen science projects where you got data collection from various groups in various ways, maybe supplemental by electronic automated collection. So I think the process you're going through, could be very useful and transferred to other projects. I mean, river flow monitoring, things like this is always going on, atmospheric monitoring and modeling. I think often if it involves various ways of measuring something, you run into the issue that you are facing, seems to me.
Yeah,
So
yeah.
it could be really good to transfer it to other ones, to other areas.
And in fact, that's exactly why I'm doing this project, is because we don't, as I said, even though it sounds like 1 million rows sounds like a lot of data, but that's a lot of data just about very few geysers. What we need is there are tons of them, and if we can find like this data, at least even first approximation. So if we can say maybe not this data is not as accurate as like the electronic data, but it's a first approximation. Then now you model your data, do any study, and if it's reasonable, given say our data is, let's say, good enough, then at least that will set up some constraints in the model. Yeah, thank you.
So is it the source of the data that causes, so there's 50,000 rows in question, right? Is it the source of that data that calls it into question, or what exactly, how do you know the data is bad?
Okay, yeah, thank you. Because people are under the impression that because it's collected by a lot of other people and with different times and stuff, so we don't really know it's bad, but we are not sure it's good.
You don't know it's good.
Yeah, and so if it's really good, if we can compare it with the electronic data, because the electronic data, part of the electronic data is about the exact same geyser, about the same variable, and on the exact same date, in the same day. So that's how, when somebody was going to do a model and say, I cleaned this data, I said, oh, this data is collected by lots of different people, different times, I don't trust it. So that's the point.
Okay, so if you have a known good row of data about a specific eruption at a certain date and time, and then you have a possibly bad row, and you want a way to compare the two, right? To determine how bad if one of the 50,000 rows, or if each of those is good, right? Is that right?
Yes, and the only problem is you can't really determine which among the 50 is good or bad unless you compare them with something good. In other words, there is no way we can say like, well, maybe the duration is more accurate than the PrePlay, but we have no evidence of that. And so that's why, like I said, when we spend really a lot of time comparing, altogether it's almost over 1 million data from the electronic data, and in the other one that the 50,000, and just try, if there is any, in fact, I'll just tell you one thing I did very quickly is I said, how about I just plot them, just to plot the data I don't want to hear, just to plot them in the scatter chart. The problem is the electronic data is very variable in a lot, because you have more than one eruption. Like I said, you have maybe 5 eruptions, but the other data you have only 1 eruption, so I don't know how you can compare them.
I have a question about the original eruption model you showed that I think you said was work that you did with your thesis advisor. And one thing that was interesting about that to me is there was a long tail to the left, which indicated that it existed in both the data and the model, right? So there was the bulk of eruption intervals that were longer, but there was a definite smaller data set that was significantly shorter interval. And I'm curious if you have a heuristic about the model or about how geysers should work that predicts why that ought to happen. Why would you have a
You
long
mean
tail?
why the difference is?
Specifically, what is it about the model that predicts a significant number of shorter interval events?
Steve, I do not know. I cannot really answer that question. I can possibly send my advisor this question. He is the one who did the heat flow. I kind of have a little bit of understanding of it, but he even told me jokingly, he said he has only used a basic language that programming that nobody uses anymore. And I told him one time, can you just show me your program so I can figure out? But the short answer is I'm really not sure. But if maybe sometimes we'll talk about it, and then I really would like to talk to my advisor to see what his take on it.
Any other questions? Yeah.
So when you save your data, do you save in as an Excel file, or you have kind of a specific data structure to store them in, specific way for your purpose? Like how you store your data?
How did I solve what?
Your data for programming. Do you just pull data from your Excel file, or
okay. How? All what I did is really in Python is you just if I have it in Python is just it has a very nice tool. It's just it would read the whole Excel book. It reads every single sheet. It reads them all, and it reads them in a what they call data frame, and it does the same thing. So I have like the workbook for the electronic data. All what I did is I just read them from Excel, because I'm glad you mentioned Excel. This is one exercise you do not want to be close to Excel, because Excel is not going to do anything. It's just like it will crash you in a minute, but that's what I did. So I read both, put them in two different data frames, and then I even averaged, because we have so many of them. I averaged one part, and then I compared the average. That's all what I did.
Any other questions? All right, let's thank our speaker.
Well, I want to thank you guys for listening.